So, hi, we come from, well, we are part of Qilimanjaro. Thanks, Eli, for the presentation. And yes, we are going to explain how we integrate different devices from different nature for doing our computations. So for this, I will start explaining our stack and giving a little bit about the different interfaces we have, the different moving parts in our system. Then Adri will focus on how we apply this with with the Slurm workload manager and why this is relevant with quantum setups. And then Victor will give an example of an application that proves that shows that our setup is actually quantum. So our stack. I'm a little bit confused with two screens. Sorry. Qilimanjaro is a full stack company. We are moving towards we try to focus on analog quantum computing, but we do all the steps in the process, from the design and manufacture of the chips to the design of the high-level algorithms that are actually used for things in general. This means that we have custom pieces of software all along the stack. So starting from the bottom, what we call backends is what we have in our labs, both for simulation and for real executions. Specifically, QuiliLab is the library we will use we are developing and using for defining our executions in the lab, for for abstracting the experiment design from the different vendors of hardware and hardware control devices. Then we have for exposing this through a Red API, we have the Quantum Lab API that interfaces the executions that come from outside with the workload manager. Then we have the Quantum Public API so that external users can send executions. It manages all the user stuff. It is always online and is a first step in the queuing of a job. Then we have Cubo Connection so that a user that is using Python can integrate. It's basically an SDK that abstracts the web communication. Finally, we sometimes use Kibo for defining our experiments and our algorithms. It is an open source library. We have contributed to it, and it's open up there. And finally, we have the application stack, which is the backbone. We put everything that we develop above Kibo. So the usual user story is that a user writes a quantum circuit in whichever way he prefers. Currently, we are supporting QaaS internally, so anything that can be written in QaaS and can be sent. That job arrives to the public API. It is stored there, database, whatever. Then he receives an ID, basic async stuff. At some point, the public API relays the execution to the corresponding lab. We have a couple of them right now. And inside the lab, it will be queued and executed at some point. The results will be posted back, and the user at that point can recover the results. Basic async web job issuing. We have two types of users. This works for the external users, for the user that is only taking care about circuits or the Hamiltonians or whatever. But then we have a different kind of users that is the lab users. Those are allowed directly to log into the labs, into the login nodes, and treat the different quantum stacks as if they were parts of a Slurm cluster. So by choosing partitions and by writing very close to by writing experiments in a way that is very close to how hardware is, and by choosing partitions, then they can choose where and how to execute their experiments. So with this, the context is kind of more or less clear. So, Adri, can start. Click this.
So this is a pointer.
Cool. So basically, what I would like to explain is to answer 3 questions. Why are we using Slurm? How are we using it? Okay. And a bit of visibility on our next steps in that regard. So first of all, let's pick a use case to understand the value that Slurm provided to us. The use case is the basic one. So I'm a hardware engineer, and I want to run quantum stuff. Okay. And we have a constraint. So due to the current stage of the technology and our current chip size, okay, the possibility of running 2 quantum experiments at the same time is not there. So if I'm running a quantum experiment and another person tries to connect to the quantum processing unit, he will mess up my measurement, okay? So to understand the value, let's think of the situation before Slurm. So if I wanted to run a quantum experiment without Slurm, what I had to do in the past was, first of all, use qubit connection for blocking remote executions, because at the same time we are working in the lab, there are remote executions coming from external users. Then coordinate through Slack with my peers to say, hey, please don't mess up my quantum experiment. And finally, I could SSH to the login node and send my thing. Cool. So after Slurm, I don't need to care about what my peers are doing, and I simply SSH and send my job. So this has translated basically in a dramatic increase in the quantum processing units availability, both for internal and external users. Now, for the how. So here we have a diagram with a bit of the implementation we have right now. So we have 3 components, basically. Okay, I don't see the pointer. Okay, we have here qubit connection. This is the cloud part. Then we got the login node and the compute node. So in the login node, we've got a shared home path with NFS, which is also here in the compute node, and which includes a quantum environment, the contextual libraries, Qililab, which is the proprietary software library of Qilimanjaro for quantum control, and then Submitted, which is the Python Slurm interface we're using. Basically, what Submitted does for us is I give to Submitted a Python function, typically a Qililab function, and then he translates. It doesn't translate, sorry. So you give it the Python function, he creates the corresponding Slurm script, okay? And then using the Slurm client installed in the login node, you can execute your Qililab code in the compute node, okay? Basically, what Qililab does is send assembly instructions to the control electronics, which in turn sends pulses to the quantum chip, okay? So that would be it. Finally, a bit of visibility of the next steps. So we aim to move toward the integration of high-performance computing and quantum computing. And the main motivation right now are hybrid jobs. This is jobs that are partially classical and partially quantum. Examples could be variational quantum algorithms or tensor networks. So why is this our main motivation? Because as Miriam very well explained, we are in the NISQ era, which stands for Noisy Intermediate Scale Quantum Computers. This is small and with errors quantum computers. And this means that quantum resources are very scarce. And hence, we need to use quantum only when it is strictly needed, okay? Then the question to answer, in our case, is, given a job that includes both classical and quantum parts, how can I split the execution of these jobs in different nodes, in classical nodes and quantum nodes? We don't have the answer yet, but this is a work in progress. So we are collaborating with HPC now to explore different approaches. So having said that, Victor, floor is yours.
Okay. Okay, so now I'll go through a practical example of how a user would run an experiment from the cloud or even in the lab. And this is going to be the CH-SH game, or if you want to get more technical, we usually call it the proof of the CH-SH inequality, where CH-SH stands for Clauser, Horn, Shimony, and Holtz which are some of the guys that popularized this inequality in the scientific world. So it's basically a demonstration of quantum effects, or something that cannot happen classically. In this case, it's the demonstration of the non-locality of entangled quantum states. Okay, so let's try to see this as a game, because that way it's funnier. So basically, you have a typical Alice, Bob, and Charlie, and you have a game where Charlie is sending some bits of information, so 0 or 1, to Alice and Bob. And these bits of information, they can follow a uniformly distribution, or they can just be any kind of distribution that Charlie only knows. And then Alice and Bob have to send back bits of information, A and B, to Charlie. And Alice and Bob will win if the AND of the X and Y that Charlie sent are equal to the exclusive OR that Alice and Bob sent. So the question then is, what strategy can Alice and Bob choose in order that they have the best chance of winning? And as we'll see, if they use quantum mechanics, they will have a higher chance of winning. And at the end, we'll also go through some of the code that we have for this. And if you have a phone and want to read the QR code, I will link you to a GitHub page with a notebook. So okay, the classical case is quite simple. We can build the truth tables. I'm always putting it. You can build the truth tables for X and Y and A, X, or B. And you will see that actually, respectively, if Alice and Bob, irrespectively of what Charlie sends, always choose 0, they will win in 3 over 4 of the times. So the best chance of winning is 3 over 4, so 75%. Now the quantum case, as expected, is a bit more complex, and that's not because in quantum we deal with complex numbers, but that's funny anyways. But anyways, so we can follow a strategy where if Alice and Bob share a Bell state or a maximum entangled state before the game begins, they can use this in their advantage without sharing any information through the game. So what they can do is imagine they have this Bell state, and if we take the ups as being zeros and the downs as being ones, this state would correspond to the superposition of the 0, 1 and the 1, 0 state. So what happens in the quantum world is that this state has some correlation, so that, well, also it has a superposition. So if you've heard like Schrödinger cat and so on, so this is it. So basically, when you measure this state, you have a 1/2 of probability of getting the 0, 1 state and 1/2 of getting the 1, 0 state. And Alice has one of these qubits, and Bob has the other one. So if Alice measures 0, then Bob will measure 1, and if Alice measures 1, then Bob will measure 0. So this is called entanglement, basically, and this is a maximal entangled state. So they can do this clever trick where if they measure in different directions or bases in their quantum space, they can do this in a very smart way so that they maximize their chance of winning. And if you do the calculations, you will see that in the end, Alice and Bob will have at most cos squared of pi over 8 chance of winning, which is around 85%, and that's higher than a 3/4. And here we use 2 properties. Oh, this was actually a GIF, so the arrow was moving, but you cannot see it on a PDF. So anyways, we're using 2 quantum properties. One is entanglement, as we mentioned, and you're also using the fact that your qubit lives in a 2-dimensional space. So even though when you measure, you're always projecting your qubit, which you can see as a vector moving in this block sphere, so the measurement will always be a projection in the vertical space, which is the 0 or the 1, but you can also rotate this around to sort of measure in what we call different bases or different directions. Mathematical formulation of this was also developed by Bell in the 70s, and you can also express it like this, which essentially you can add up the different bases in which you measure your Bell states, so that you will see that if you add it up in this like specific way, you will have a higher bound of 2 in the measurement and the sum of your respective values, but you will have an upper bound of 2 times the square root of 2 in a quantum case. And if you're interested in this, it's very interesting also from a philosophical point of view, so you can check out the Stanford's Encyclopedia of Philosophy for the CH states inequality or the Bell theorem, and you also have the Wikipedia page, of course. So now we can switch to notebook, we'll have to do some classical interaction to scroll through. We'll see if it works. Okay, it's going great. Yeah. But I guess the whole presentation collapsed.
Okay.
There we go. Yeah, so as you can see, this is our regular Jupyter notebook. We are doing our imports, then we're defining, no, go up. Okay, so here you define your API, you have a username and an API key, so this is where the whole Kibo connection part comes in. Yeah, then we define the experimental parameters, which in this case, we just select one of the 4 possible Bell states. We also have defined some gate fidelity, you will see why this. Yeah, then we build the circuits, and I will not go into detail over this, but essentially you build a circuit to create the Bell states, you build and then the circuits in which you measure, and if you go to the next cell, yeah, then you just run the circuit. So you create a list of circuits, and then you call your API.execute with the number of shots that you want to run for the circuits. You can also give this a name and a summary. And then you wait until the execution has finished, and if you just put these object results, then it returns the whole results, which, as you can see, is just a list of your probabilities of your 2-qubit state. And that's long list. Okay, so then after that, you do like some post-processing of the data, and then we also run a simulation to calculate error bars, and then you get the plots, which I will explain. So here we're running this particular order Bell state, which is a different one from the one I presented. This is the 0, 0 plus 1, 1 state. And here you see 2 plots. So one is the raw data, and the other one is the readout corrected data. This is a common procedure in quantum experiments. So because your measurement gate, actually it was in one of the presentations earlier in which they talk about something that they call spam errors or spam noise. So essentially, because your measurement gate has some fidelity, which is not 100%, when you read out, you always get like some errors in this readout, and you can correct for this. It's sort of like a contrast correction. But well, anyways, you correct for this, and then you see that when you rotate your state around, you get past this classical bound of 2, and you approach the 2 times square root of 2 of the quantum bound. And yeah, it's a very nice experiment to see many quantum effects, and that's it. I don't know if you have any questions. Well, afterwards. So I'll answer the physical questions, and the cloud team will answer the cloud questions.
Thank you for this kind of presentation. So, no question from the audience? No, I have questions, of course. So that is a little bit tricky because I'm participating in that, but the way that you apply Slurm to solve the solutions, so can we change at any moment Slurm by another workload manager, such as LSF, PBS? Do you know if Submitted can handle that?
I think right now we're using Submitted, as I commented, and this is specially designed for Slurm.
Mm-hmm.
But I suppose there are other Python libraries that could serve as an interface for other workload managers, but I don't know them. So it would be a lot of work to do it if I had to do it.
Can I make a note? Yeah.
I think that with respect to that, as this is integrated with what our users are doing in the lab, is not only the integration with the API, the most difficult part is probably teaching everyone how to use that and how to change. So yeah, it can be done easily, but then there's the human science.
So any other question from the audience? Just one.
So we've seen integration of Slurm with Quantum. Are we doing Kubernetes on Quantum as well?
Well, we are working on it. We are working on not on Kubernetes right now. We are using Dockers for microservices. We are trying to make it as as easy to deploy as possible, because at some point we will have more labs. We will maybe even have labs outside our premises. So yes, we want that to be as easy as possible, and we are trying. We took notes on the first presentation.
Okay, then maybe something that you can explain to the audience, because I know that Qilimanjaro is manufacturing analog superconducting qubits that are different from the one from IBM that are digital superconducting qubits. Can you explain to the audience in a 5-year-old level the difference between the two technologies?
Yeah, okay. So the point of analog is, you can imagine that when you have gate-based, you have these sort of discretized pulses that you send as gates, in the superconducting case at least. So when you do analog, it's sort of like you, instead of one single gate or many gates, you have a whole waveform which you use to evolve the system over time in a continuous manner, continuous as much as the resolution of your pulses can be, but anyways, it's continuous over time. And it also works on a different principle of quantum mechanics, which is called the adiabatic principle. That's why we also call it adiabatic quantum computing. And it essentially, well, if you know what a Hamiltonian is, or you know what a ground state is, and if you don't, I apologize, because it's, but anyways. So basically you have your system in a like sort of relaxed state, which is the ground state, and you want to evolve this very, 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 very slowly so your system doesn't get too excited to a higher energy level. And then if you do this properly, you will be able to change from one Hamiltonian to another, and the system will remain in its ground state. And if you do this, then you can encode a difficult problem as the final Hamiltonian, and then when you do the readout of this final Hamiltonian state, you can get a solution for your problem. Hopefully that's clear.
And which advantage does it have in front of analog, in front of digital?
Advantage?
Yeah.
Oh, well, so first of all, one problem that you have in gate-based is that you are limited by the decay time of your qubit. So if you're working exciting qubits up and down, then because the qubits have some decay time, this sets like a higher bound on how long your circuit can be. In analog, because you're always working on the ground state, you don't have this problem of the system decaying from a higher energy level to the ground state, because you're already there. It also has other advantages, but these are more related to the specific qubits that you're using. So you can also like operate, you can also do this evolution of the system faster, because the qubits are designed in a special way that the energy levels are more separated.
Can I add something?
Yeah.
I'm not a quantum engineer, okay, but the translation to the business side of all this quantum thing is digital requires error correction. This is very difficult, and everyone is working on that. And analog doesn't require error correction. So in theory, I know, but the summary is...
Are we going to do a rap battle? No, something I forgot to mention is because of the design of these two different kinds of paradigms, which are actually equivalent. So, I mean, there's paper proving that both of them are universal. But anyways, so say gate-based is better at solving usual problems where you have like differential equations or Fourier transforms, whereas analog is better at solving optimization problems. So in the near term, you can also find more applications for analog, because you can, for example, like design a specific chip for a specific optimization problem, and this in the near term you'll need as much error correction for this. So it's it has actually more potential in the NISQ era, for example, or what people call the middle NISQ, which is not NISQ anymore, but just like the middle stage between NISQ and tolerant fault quantum computer.
So I can keep talking to that guys 4 years. So just to cover a little bit, because we have only a gap to cover the schedule. But I have more questions. And related to the fabrication, because I know that Qilimanjaro has a team that handcraft the chips. So can you explain a little bit? Because there is no industrialization on the fabrication of quantum chips at any level.
So what's the question?
So what is how it's made?
How it is made?
Yeah, in few words.
Victor,
I mean, it's an experimental process. So you have some people who have clean rooms and white rooms, and I mean, I'm not a design engineer, so I don't fully know. But essentially, you can simulate. You can. I mean, you design a circuit, then you can try to simulate this in several different ways. It's more precise than the other. Like, so in semiconducting qubits, you can simulate like each single step of your wire, and then do like a full simulation of the chip, see how that goes, and then you send this chip to fabrication. Or if you have a white room or like the facilities to fabricate, you fabricate this by using like I think it's like some kind of deposition. Well, I don't know the exact method, to be fair. Sorry. But yeah, I mean, it's same way. It's semiconducting, so it's not so different from the way that you would fabricate an experimental semiconducting chip, because you're working with well, superconductors actually, but that it's similar. So I don't know if that answers the question. But then, I mean, you fabricate this. Well, you design, you fabricate, then you get like many like a wafer with many same samples of the same chip, and then you start testing them, because some of them are better, because it's, I mean, it's hard to, these are designed so it's easy to reproduce, but even then it's hard to have always the exact parameters. So you have to test these, then calibrate them, and yeah, hopefully usually we make them so that you can sort of tune them to the, so even if the parameters are not always the same, you can still control them to operate like I don't know, a couple of qubits in a controllable way.
And so the difference of Qilimanjaro in comparison to other companies would be that our approach is ASIC, which is specific. So we aim at designing chips and fabricating them that are specialized in some specific tasks, such as special types of optimization problems. So hopefully this whole process of characterizing the chip, calibrating, and getting good results must be easier if you are designing from scratch the chip for that, right?
And also we do the full stack of quantum computing. So we go from design to all the way to the top of algorithms.
Why not? Because you said all the magic words now.
Oh, it's true. Yeah. You did, so what's up under, sorry, is that? I'm more serious than us.
Excuse my ignorance, but you mentioned solving differential equations on, I think it was digital quantum. So how far has the technology got? What can, just give me an idea, because I don't follow the space, but how far is it? I mean, have people been able to solve large-scale differential equations, or?
Well, I think that the next talk was from IBM, so they probably know better. But as far as I understand, I mean, not very far, even though we are like every time we are closer. So, I mean, if you check like of course, number of qubits is not a good indicator of how far technology is evolving, because you also have to make better qubits. So like coherence, noise, these really matter. So if you have 100 bad qubits, this does not matter much. But if you look at the curve of how many qubits you have in like a quantum computer from say like Google or IBM, this follows more or less like an exponential, or more so if you want like 2 to the power of something. So, I mean, we haven't really got to the point in which we have like practical applications in which you cannot efficiently simulate your quantum computers. But we are getting, well, as far as I know, we are getting closer to it. So now we are in the NISQ era, which is the near noise intermediate quantum system. And some people are starting to talk about already like I think it's like not intermediate, but it's like a middle layer. So you already have like might have some practical applications you might be able to use like in 4 years time, or maybe less, hopefully, like your chip, not as a universal quantum computer, but as a sort of like an accelerator, like you would use a GPU, for example. But yeah, I mean, you can still not run Grover's algorithm in a relevant way, or run Shor's algorithm, which is everyone's goal. For that, you would need with the standard gate-based qubits, I think the estimation is like millions or hundreds of thousands. So like a lot, and you're already sitting at 1,000. So I don't know. Optimistic people say 10 years time you'll be able to break Shor's algorithm, but not optimistic people say 30 years. So you have quite large uncertainty.
Any other question from the audience? And no question from the moderator. So let's thank again to the speakers.